So I'm going to go over the final project for the chi-squared goodness of fit with equal proportions. Specifically, what we have right here is data on the number of job openings based on company size. And what I want to know very specifically are the number of job openings based on company size, are they proportionate to each other or are they different than each other? And so we're going to get started. We've got companies that the size of the company is more than 5,000 employees, 1,000 to 5,000, 501 to 1,000, 201 to 500, 51 to 200, and less than 51 employees. And how many companies are there that are in this, that are in each category? So what we're doing here is, first of all, we're going to come right here and we're just going to walk through this. Also, this is the company size specifically for companies in San Francisco, I believe. San Fran. We'll go San Fran. Okay, so research question. Is the proportion of job openings in San Francisco equally distributed by company size? That's what we want to know. And once we do that, we can start going through everything else. So right away, I can tell you, because we're examining difference in counts between categories, we are able to go to the decision tree. And we can say, okay, what are we dealing with? Are we dealing with continuous data from samples or a population, or frequencies of categorical data? We're definitely dealing with frequencies of categorical data. And then I'm comparing observed frequencies distributed to an expected frequency distribution. Are they expected to be equal? If yes, come over here. If no, come over here. They're just a little bit different, but they're pretty close to exactly the same. So we do expect them to be different, so we're going to do chi-squared goodness of fit for equal proportions. So you've got this right down here, the goodness of fit for equal reference. This is the final project example sheet. And so you've got all of this wonderful information right here that gives you more information on how to do all of this, and how to write up the hypotheses, how to the purposes of the test, so on and so forth. So going a little bit further down, chi-squared goodness of fit for equal proportions. We have all of these, and we want to know, are they equal? And so the first thing that we have to do is find out let's fill all of this in really quick. The total number of job openings. So in order to do that, we do equals sum, which hopefully I've already done this for you, but so we have that. This right here is the total number of job openings in San Francisco, and then we are going to, there's a total of 6 categories here, so we've got to divide this by 6, so equals this divided by 6, and the reason why it's 6 is because there's 6 categories, so therefore we expect them all to be equal. And if we expect them all to be equal, if we expect them all to be equal, then they all need to be Control C, Control V. Then they all need to be the exact same and add up to exactly what is observed. Okay, so we're gonna drag this down. Okay, and fill without formatting. And so we expect all of them to be 22,983. Okay. And so the next thing that we're going to do is we are going to find the relative frequency of each of these. So we're going to do equals this, the frequency of 50,000 plus companies, divided by the total number of companies. And I'm going to drag this down, and I'm going to fill without formatting because I don't like all those lines. And so we've got the relative frequency of each company. So, but let's come back over here. So now that we did all those calculations right there, We're going to do the total number of categories. We have 6 categories. The declared alpha, I want to know what 99% confident that my answer is correct, or I only want a chance of saying that there's something, that there is a difference when there's really not a difference. I only want a 1% chance of that. And then chi-squared is a test that we're running. Next, degrees of freedom. Degrees of freedom very specifically is the number of categories minus 1. So it's going to be equals 6 minus 1, which is 5. And then next, is it equal or unequal? And that's going to be equal. And then the total number of observations. The total number of observations is right down here. It's not 6. It's really easy to think that it's 6, but it's not 6. It's actually 137,899. It's the total number of job openings, the total frequency observed. And so we're going to right-click and we're going to paste values. And now we're going to calculate for chi-squared. But before we get into this, we'll get into this in just a minute. Let's go through these and answer this information to make sure that we're all on the same page and that we're doing things correctly. So first of all, the research question, like I said, is the proportion of job openings in San Francisco equally distributed by company size? That's great. We want to know, are they equally proportionately distributed? Next, to determine if the observed frequencies of job openings in San Francisco are equally proportionate between company sizes. That is the purpose of what we're doing. So in other words, give me the textbook definition. So coming right here, to determine if observed frequencies is equally proportionate between categories or groups, you can literally just copy and paste this, just put your information right alongside in there. So you notice I do the same exact thing, but I put San Francisco and then company size. Excuse me. And then what am I expecting? I'm expecting that job openings will not be equally proportionate between company sizes, is what I'm expecting. Next, we're going through the assumptions. Once again, goodness of fit for equal. Here's the assumptions: that there's one categorical variable, that there's independence of observations, that there must be an expected frequency of at least 5 in each category, and that the expected frequencies are all equal. So coming back over here, what is the one categorical variable? The one categorical variable is company size. So if you look right here, we've got company size right here. And the categories are 1,000 to 5,000, so on and so forth, all the way. So I tell you the company size is, the main category, and the different categories inside of there are the sizes of the company. Assumption 2, describe how you know that the observations within each group are independent of each other. Job openings fall into one of these groups and cannot be in more than one group. It's not complicated. Just tell me, the very obvious answer. Tell me how you know that they're independent of one another. Next, ensure that the expected frequency is at least 5 for each group. So we're coming over here and we're saying, is the expected frequency at least 5 for each group? And the answer is yes, definitely yes. The minimum expected frequency is 22,983. If it's less than 5 for a particular group, you just can't trust the results. Okay, so the minimum expected frequency is 22,983. And then are the frequencies between each group expected to be equally proportionate, or proportionate to something else? And we're saying the proportion being tested against, we're expecting it to be equally proportionate. Okay, now when we get into the null and alternative hypothesis, it's actually a little bit different with the null and alternative hypothesis. The null and alternative hypothesis compared to, what's that called? Compared to the other ones. And the reason why is because you have to write it out. Okay, so I'm going to zoom in a little bit. Actually, I'm going to come right up here so that you can see it. The null hypothesis, once again, null hypothesis means that there's no difference. Alternative hypothesis means that there is a difference. So right here, there is no difference in the proportion of job openings in San Francisco based on company size. This is the null hypothesis. There is no difference. The alternative hypothesis is there is a difference in the proportion of job openings in San Francisco based on company size. And so you've got one where it says no difference, one where you say that there is a difference. So tell me, what are you expecting there to be a difference between, and based on what? What are you expecting there to be no difference between, and based on what? Okay. Next, chi-square inverse right tail. This is the formula that you need to use. So we're going to do equals chi-square inverse right tail. So what this does is it returns the inverse right tail probability of the chi-square distribution. So in other words, if I do this and I say, okay, I have a probability, the probability of it being on the right tail, I want an alpha of 0.01, so the probability of being on the right tail is 0.01. And the degrees of freedom, remember, I think we had 6 categories, so the degrees of freedom is 5. So we're going to go like that. And right away, it gives us our test critical value. Our test critical value. So a chi-square distribution is only ever a right-tailed test. Notice I don't ask you for the tail. The reason why is because it's only a right-tailed test. So if you get a test critical value greater than this, or sorry, if you get a test calculated value greater than this, then it's going to be, then you're going to reject the null hypothesis. If you get a test calculated value less than this, then you're going to fail to reject the null hypothesis, which I put right here. If chi-squared calc is greater than 15.086, reject the null hypothesis. If chi-squared calc is less than or equal to 15.086, you fail to reject the null hypothesis. So now we're going to get into actually calculating the test calc value. So I'm going to come over here, and I know that in another video I actually give you all, I just calculate everything for you, and I used to do that, and I'm going to tell you something. I really don't think that it helps me, or it helps you for me to do that for you. So what I'm going to do is I'm going to show you step by step how to do this. So I'm going to do Control C right here, and I'm going to do Control V, and I really do my best to make it as easy as possible for you by putting the steps right up here. I'm going to zoom in a little bit. You've got each of these columns. You've got frequency observed, frequency expected, frequency observed minus expected, frequency observed minus frequency expected squared, then divided by frequency expected, and then so on and so forth. So we'll get there. So first step, you have all the categories. You have the observed frequencies in those categories, and you have the expected frequencies in those categories. So the first step is you're going to calculate the difference between the observed and the expected. So we're going to do equals frequency observed minus frequency expected. And it tells me, okay, the difference between what's observed and expected is 27,278. Great. Now let's drag it down, drag that formula down, and that formula is now going to, you notice it says frequency observed minus frequency expected. Now it's this frequency observed minus frequency expected, same thing. And when you drag the formula down, it does that for you all the way down. This is like one of the most satisfying things for people who just love formulas. Next thing, just equals frequency observed minus frequency expected, square it. And what you're doing here is you're getting rid of that negative, right? You're getting rid of that negative and you're making it all positive, and you're also putting it into the squared realm world. So frequency observed minus frequency expected squared. And then the very next step, we do equals frequency observed minus frequency expected divided by the frequency expected. What you're doing here is, let's see here. You're basically, well, you've got the difference, you're squaring the difference, and now you're dividing the squared difference by the expected score. Okay. And there's something wrong there. Oh no, there's nothing wrong. The reason why is because, oh, hold on. Yes, no, there is something wrong. Frequency expected. I don't know why. I was like, it's not supposed to be negative. I just clicked on the wrong row, so it's not supposed to be negative. So you are dividing it by the frequency expected. And then after you divide it by the frequency expected, you are going to add all of these up, because these are actually all of the relative contributions, or all the contributions to chi-squared. Okay, so what we have is frequency observed minus frequency expected squared divided by the frequency expected, and we did that all the way down. And these are all of these individual categories, individuals' contribution to that chi-squared value. Okay, so this is a chi-squared value, and I will tell you right now, this chi-squared value is huge. Absolutely massively huge. And just to show you how huge it is, I'm going to do equals chi-squared dot dist dot right tail, and we're going to put in the chi-squared value. So I just put in put in G40. What I just did there is I clicked above it because I can't actually click on it. It's really annoying. You can't click on it. So I clicked above it and just went down 2 times. Then the degrees of freedom is 5, right? Because there's 6 categories, and it basically says the probability of it is 0, or p is less than 0.0001 is another way of writing it. Okay, and then the degrees of freedom, just once again, 1, 2, 3, 4, 5, 6. So degrees of freedom is 5. Okay. Next is some more information on this right here. Basically says, hey, you know what? There is a difference. Great. I'm so glad you let me know. There is a difference. They are not all equally proportionate. Did you really need my help to find that out? Maybe, maybe not. This is massively huge. But I don't want to stop there. I want to know what's contributing to that difference. So in order to find out what's contributing to that difference, I'm going to find out the proportion that each of these categories contributes to chi-squared. So I'm going to do equals this contribution to chi-squared divided by the total chi-squared. Okay, and I'm going to put the $sign right there. And I'm just going to drag it down. Okay, so what we see right here is this category, 5,000 plus, contributes 68%, contributes to 68% of the chi-squared value. This contributes less than 1% to the chi-squared value. Then 501 to 1,000 contributes 23%, and then all the rest of them are all less than 10%. Really, I only care about interpreting the ones that are greater than 10%. It's not enough to just say that it contributes 68% or that it contributes 23%. I want to know how different is it from the expected. So the last step that I'm going to do is do equals percent different from expected. The way that you do this is frequency observed minus frequency expected. So this column right here. And then you divide it by the frequency expected. Okay, and you just drag it down. And what this says right here is this contributed 68% to the chi-squared, and it differed from expected by 118 or 119%. Okay, it was 119% greater than what was expected. So what you observed was 119% greater than what you expected. What you observed was 8.8% less than what you expected. What you observed was 69.5% greater than expected. What you observed was 33% less than what was expected, and what you observed was 17% less than what was expected. But you don't just interpret this, you have to interpret these two together. Okay, these two together, because you only interpret it, only the ones that contribute a lot to the chi-squared are the ones that you should be interpreting. So just be paying attention to that while you do your write-up. And so we're going to go right there, and we're going to go right there, and I'm going to highlight those. Okay, sorry, Lizzie's going to be joining me, so if you hear her, see her, she's just chilling with me. So we're coming down here, we've got the, we have the contributions to the chi-squared right here. So this right here, very specifically, is the contributions to chi-squared. The contribution to chi-squared, and then this right here is the the relative contribution to chi-squared. So the value contribution to chi-squared, the relative contribution to chi-squared, and then this right here is the percent that it differed from what was expected. Okay, so as we go through, we'll add that up. So, but next, just like with all of our other tests, with all of our other tests, we have the ability to calculate the effect size or how noticeable this actually is. Remember, just because we have something that's significant, even if it like appears to be really significant, does not necessarily mean that it is actually noticeable or that it's practically significant. So we're going to bring in all this information. We've got chi-squared, we've got the number of observations, which is, you know, the legit number of observations right there. Shh, hold on. And then we've got the degrees of freedom, so it's going to be equals 5. And then we're going to calculate Cramer's V. And so in order to, hold on, don't grab that. In order to calculate Cramer's V, we've got to do equals square root. Okay. And then we've got, I'm going to put another, there we go, chi-squared divided by n, or actually divided by, I'll put another parentheses, n, and then multiplied by the degrees of freedom. And then let's see here. There we go. And so that right there is Cramer's V. In order to determine if Cramer's V, if it's significant, what we need to do is come on over here and look at the relative, or look at how it compares to, you go down to the degrees of freedom. So the degrees of freedom, which is right here. So we've got 5 degrees of freedom, and you compare it to these right here, 0.04, 0.13, 0.22. So what we know is, because it says 0.26, that this is a large effect size. This is a large effect size. So this is a difference that is also very noticeable to the naked eye, even without statistical anything. So that right there, you know, fill all that in right there as well. And let's see here. So I put the test calc value in there. Don't notice I say I've got this. I use the chi-squared.dis.rt. Don't put 0. I really don't want 0. What I really want is p is less than 0.001 or 0.0001. Either way is fine, because 0 is not actually true. Technically, it's probable, it's possible, because it happened. It's just extremely improbable if you assume that they're all going to be equal. Okay, so when you're interpreting it, and this is a little bit different than the other ones, because, yeah, this is a little bit different than the other hypothesis tests, because I have you do your interpretations right here. Hold on. Okay, so the probability of this result, assuming the null hypothesis is true, is virtually 0. As the p-value is less than 0.001, the results are statistically significant. Okay. Next, make the hypothesis decision. As the chi-squared calc, so we're comparing the chi-squared calc to the chi-squared crit, right? So we compare this calc value to this crit value. As the chi-squared calc of 47,263.538 is greater than the crit value of 15.086, we reject the null hypothesis, which means that since we're rejecting the null hypothesis, we're rejecting the idea that there's no difference between the two. Okay, and then interpret chi-squared. The chi-squared calc of 47,263 indicates that there is a difference. That's all that it does. Hold on. Oh, that's all that it does. That's all that it does, is it indicates that there is a difference. So often people stop just at chi-squared. Hold on. Okay, so the chi-squared calc, that's all that it's doing, is telling you that there is a difference. That's it. And like I said, most people stop right here, and they never do any of the other steps. I don't care that there's a difference. It's completely pointless for me to tell you that there's a difference. You've got to be able to interpret. So they're only interpreting this one column right here, this chi-squared calc column. That's all that they're interpreting, and they're saying there is a difference. Whoop-de-doo. Okay, what you need to do is you need to be able to tell me where does that difference come from. Okay, or sorry, basically what is the difference. So this tells me what is the difference, and where does that difference come from. It differs by a certain amount, like an actual frequency. It differs by an actual frequency, and then it also differs by a percent. Like I said, this is 69% less than what was expected. This is 118.69% greater than what was expected. And so we've got to interpret that as well. So right in here, interpret the percent chi-squared with the percent differed from expected. By interpreting the percent of chi-squared, 69% of the contributions attributed to the difference in proportion of job openings is based on company size is attributed to companies larger than 50,000 employees. Okay, what I just said right here is by interpreting, percent chi-squared. So by interpreting this right here, this column right here, we can tell that 69% comes from 50,000 or 5,000 or plus employees. And we're also going to indicate that 23% occurs from this category, but we're not even going to mention the other ones. The reason why we're only mentioning those two is because those are the only two that are above 10% right here. Those are the only two that contribute more than 10% to the chi-squared value. And frankly, if your chi-squared value down here is not statistically significant, these aren't even important. Okay, this is the first thing. This has to be significant in order for any of this to be important. So coming down here, so there are more than 27,000 job openings, more frequent than what's expected in that category. This is 119% more than what's expected. Second, companies with between 501 to 1,000 employees contributed 24% of the chi-squared value with only 7,002 openings. This is about 16,000 openings less than what's expected, which is the 22,983, which is about 69.5% less than what's expected. Notice that what I put in there, I put the actual number of openings that they differ, or the frequency that they differ by. So the 16,000, I put the frequency that they differ by, the expected, and how much it differs by. And this is just really, this square right here is so important. Without that, the chi-squared value means really nothing. Then the effect size, hold on, sweetie. The effect size is also really important because it says, we already indicated this, that it is a large effect size, and because it's a large effect size, we can actually see and know what's going on there. Next, a chi-squared goodness of fit test was run. So essentially all that I did here, what was run, comparing what was the result, the p-value, give insight about possible factors. So let's look at, we already did the majority of this. By interpreting the percent contribution of each category, 69%, and it says, hey, this is what contributed to it. These results are very noticeable. So these are the factors that are contributing. Okay, mention how noticeable they are, and how should results be used. Okay, these results should definitely be used to provide insight to those who can benefit from this information. This is where you're going to want to put the information about your client. This is how they can use it. Okay. One more thing that I forgot to mention is you do need to actually make a bar chart like this. Okay. This is a really beneficial bar chart. It shows you the difference between observed and expected. And frankly, this is one of the easiest things that you could possibly make. And I'm going to show you why. And I don't say that just to give you a hard time, if it really is not that bad at all. Okay, so with this bar chart, we're going to come over here and we're going to say, we're going to highlight the category name below. Let's company size. Okay, so company size. Then we've got observed and expected frequency. We're going to highlight this entire table, and then we are going to do insert. And you've got a choice of a histogram or a bar chart. Make sure that you do your bar chart. Okay, so we're going to do a bar chart right here. And then you've got the observed frequencies and the expected frequencies. And then make sure that you put a good title in here. And then you can move it. This requires sometimes two hands. And I'm just struggling a little bit with that right now. But move it down here to where the bar chart is. And then, spread it out. So like you notice, I put comparison of job openings based on company size. And then you spread it out to make it look good. And so that way you can really understand exactly what's going on there. And then in your interpretation, it would be really good for you to interpret the bar chart and say, based on the bar chart, you can clearly see... Based on the bar chart, you can clearly see the 5,000 plus companies, how it is significantly different than the other. So that's how you would do that, and then just make sure that you write all this up with quality, quality in your explanations, that all your math is correct, and this is probably one of the easier ones to do. Big thing, just make sure that you don't make sure that you don't accidentally do the histogram instead of the bar chart, because it's going to drive you nuts. Other than that, hope that this works well for you. Thanks.